Can you guys hear me now? Okay, good.
Yeah.
Good. All right, I forgot to plug in my headset, so that's why you didn't hear me clearly, but it's good now. So we'll get started, and then the first thing I would like to talk about is I put the Zoom meeting link here on the Moodle page here. So you don't have to look into your email every time. You can just open the Moodle page here and then click on the link, okay? Or you can actually, if you know the meeting ID, you can, whenever you start the Zoom, you can put in the meeting ID, okay? So it will be the numbers at the end of link here. So if you click on that one. Also, I put the office hour Zoom link over here next to it. So if you want to ask me questions, one by one virtually, so we can do like on Zoom as well, so we can do like video conference in that way, okay? So with that, I would like to point out that we have homework due on Wednesday, okay? So about 2 days from now. So I see some of you guys have finished your homework, but many of you guys haven't actually started, okay? Or haven't started typing your answers on the expert here. All right, so that's on the links I post on Moodle, and then also the homework dues, okay? So so we'll continue checking on magnetism here today. So after today's lecture, I think we have covered most of the content that you guys need to know on the homework 7, but after today's lecture, and then it should be all covered, okay? All right. So last time we talked about if we have a loop that carries current inside a magnetic field, then there will be torque on the loop, okay? Because there will be forces on parts of the loop, and then that will exert torque about an exit, okay? So the torque, we actually derive this, but we'll just look at the final conclusion here. So the torque on the loop is going to be equal to the current the loop carries times the area of the loop and times the magnetic field strength, okay? That'll be the total torque when the loop is actually, it lies in the same plane as the current, as the magnetic field. So that's what we have, okay? Otherwise, if there's an angle between the normal direction of the loop and then the magnetic field, okay? So on the right figure here, this is the top view of what we have. So you have looking from the top of the loop here, so you only see the top side of it, okay? So if the normal direction of the loop plane has angle theta with respect to the magnetic field, then the torque is going to be equal to I times A times B times sine of the angle theta, okay? In the previous page, when the 2 has an angle as 90 degrees, then sine of 90 goes to 1. So we didn't have the sine over there, but it's because sine 90 goes to 1, okay? More often, you would have many loops stacking together, and then they would carry the same current. So if that's what you have, then the loops overall will have a torque of n times of this, okay? So you just multiply by n turns if there are n turns of loops. So that's the last equation at the bottom here, okay? We also talk about for a current carrying wire, there will be magnetic field produced by that wire. So if this is a straight wire, then the field produced by it will be having the same length, the same distance away from the loop, okay? So you'll expect the circular magnetic field here produced around loop, and then at any distance you will have magnetic field, okay? So the strength then is proportional to the current and inversely proportional to the distance r, okay? So you can actually use Ampere's law, just like we use Gauss's law in the electric field. So in magnetic field, you use Ampere's law, which says you take the strength of the magnetic field at a certain point, and then times the path, the small increment in path. So it will be tangential direction of the B field times delta L, the small increment of the length. And then if you go through a closed path, that means you are doing summation of that. Okay, that should be equal to a constant number called mu naught, which is the permittivity of the free space. And then that's equal to 4 pi times 10 to the negative 7, all right, times the current enclosed. Okay, so this circular closed path enclose a current I. Okay, so that's what you have. So with that, you can actually calculate what's the magnetic field by a wire. Okay, so for a straight wire, then the magnetic field is going to be equal to mu naught I divided by 2 pi over R. Okay, so that means magnetic field is proportional to the current and the inverse proportional to the distance to the wire. Okay, and then the direction of the magnetic field will be determined by the right-hand rule 2, where you put your thumb in the direction of the current, so then the 4 fingers will curve in the direction of the magnetic field at any point. Okay, so in this case, you can see it's counterclockwise as the figure shows here. All right. Now a lot of times you may have current not in a straight wire, but you might have current in, say, in this case, in a circular loop. Okay, so on the right figure over, left hand figure over here, so you have current inside this circular loop. Okay, so then you can use right hand rule. You can determine that at any point, say over here, you align your thumb in the direction of current, so then you can see about at the middle of the loop, the magnetic field will be going upward. Okay, so you can turn this around, your right hand around the loop, you'll see that that will be true that inside the loop, the magnetic field is going to be pointing upward in this case. Okay, if this loop is lying in the horizontal plane, and then you have a current in this direction. All right. So in this case, at the center of the loop, so if we have loop, this is a particular case. Okay, you can actually get this result mathematically by using calculus knowledge. Okay, but we are not going to do that because we are not a calculus-based class. So then the strength at the middle of the loop. Okay, so that means at the middle of the circle here, at the center of the circle here, it's going to be equal to mu 0 I divided by 2 times R. Okay, and then at any places other than at the center of the loop or the circle, then you would determine that strength particularly. But for a particular case of if you have a circular loop carries current at the middle of the circle, this is the strength of the magnetic field produced by the current. Okay, so B is equal to the magnetic field is equal to mu naught times I divided by 2 times R, where R is the radius of this loop. Okay, and then on the right hand here, this shows you what will be the magnetic field line look like, all the magnetic field look like. Okay, it's going to be indicated by this red lines. Okay, so that will be the magnetic field produced by the current carrying loop. Okay, and then again, this is a particular case. Okay, so for other shapes of loops, then we'll have to look at a case by case scenario. Okay, but in this class, this is the particular case we want to know. All right. All right. So now I mentioned a lot of times you actually will have multiple loops stacking together. So this is the case here. So a device look like this. It's called a solenoid. So this is a device that is used very commonly when you have a circuit. Okay. So this device, you can construct this device by wrapping a very long wire. So you imagine you have a very long wire, and then if you have a cylinder, as the figure shows in the middle here, you will actually wrap the wires one turn by one turn, wrap through the cylinder. So then you have this device look like here. So if you look carefully, you can see there's wires loop by loop wrapped around this guy. Okay. And then the two ends of the wire, the this is just one wire, will be the two terminals here. So you can actually send current into these two terminals, which is indicated by these two knots over here. Okay, so this is the actual physical picture of a solenoid. So what happens is, if you can look at on the right figure here, this is what happens. You are going to send in the current from one side, and then current is going through each of these turns of coils over here. Then we'll exit on the other end over here. All right, and for each single of the loop, you can see what we talked in the previous slides, that it will generate magnetic fields. For so many turns of coils together, then the magnetic field is going to be enhanced. Okay, so you can see this, the blue curves with arrow indicates the magnetic field. So you can see inside the solenoid here, you will have very dense lines of magnetic field lines. So that means inside the solenoid, the magnetic field is actually very strong. And then outside, just outside the solenoid over here, you can see actually the lines are very thin, or you have very few lines over here. Okay, so that means the magnetic field strengths are just outside the solenoid is very small, or a lot of time we can just assume it's close to be zero. So it's very negligible. All right. Okay. So now when we have a solenoid like this, let's see what will be the magnetic field inside the solenoid. Okay. So because that will be where the magnetic field is going to be strongest. Okay. So we'll put our interest on that region. Okay. So inside the solenoid, so this is what we are going to do. We are going to, or let me just go back over here. So on the solenoid here, we are going to just cut this through. So we'll just see a cross-sectional of the solenoid over here. Okay, so then we'll just see the cross-sectional of it from the middle. We just cut it off, okay, vertically into half. Then this is what you are going to see. So you are going to see just cross-section of the coils. Okay, this is from the top, this is from the bottom over here. And then the current is going to be indicated by either dots on the top here, and then at the bottom here is the crosses. Okay, so that means the currents from the top of the wires is going towards you, or out of the board or out of the screen here. And then at the bottom here, it's going into the screen. Okay, so this is where the current is running. Now, we can use Ampere's law here to determine what will be the magnetic field inside the solenoid here, okay? So we are going to draw a closed path, which in this case will take a rectangular closed path, okay? So we are starting from some point over here, then there's this loop, this segment of loop, and then there's this one, and this one, okay? Now, inside the solenoid, this is where the magnetic field inside here is what we are interested at. So over here, B field is parallel to the path of the loop. So you'll be doing B field times the length of this guy. We call it L, okay? Now, this is on this part. So this is this guy here, side one here. Okay, so overall, this is summation from all the four sides, okay? So the first side is going to be B parallel times delta L, which is L, all right, which is L. On the second side here, you are going to do B parallel times to the delta L. So that means you should take the parallel component of the B field to the segment. Okay, so that means this guy. Now in this case, because B field over here is perpendicular to this segment of the rectangular part, so then the parallel component of the B field should be 0. Okay, so on this side, B times delta L should be 0. Okay. Also on this side over here, now B parallel over here, just outside the solenoid, we say it's very small, B is very small. So it's basically 0 times L. Then it should be also 0. Okay, so this guy should be also 0. On the fourth part here, B parallel times the delta L, because B is perpendicular to delta L. So then B parallel to delta L should be 0. Okay, so again, this would be 0. So if you apply Ampere's law to this rectangular closed part, you end up with summation of B parallel delta L is going to be just B times L. Okay, that should equal to mu naught times the current enclosed. Okay, now you have n numbers of currents that is enclosed by this rectangular. Okay, so these are the currents enclosed. Okay, assuming this is n numbers of coils here. Okay, so then you get this relationship: B times L equal to mu naught n times I. So then B field will be equal to mu naught n times I divided by L. Okay, n divided by L will give you small n, which is the number of turns per unit length. Okay, so this is the number of turns per unit length, or number of turns of coils density. Okay, turn density of coils. So then for a solenoid, this is what you have. Okay, so either this one or this one. Okay, sometimes a problem will give you how long is the solenoid and then how many turns you have inside. Sometimes it will just tell you what's the number of turns per unit length. Okay, or that means sometimes it will give you small n. Sometimes gives you capital N and L. Sometimes gives you small n. So you want to be careful about that. Okay. All right, so this is the equation you would apply to calculate a magnetic field inside solenoid. Okay, so let's look at one example here. Okay, so this one says if you want to construct a solenoid, you wrap insulate wire uniformly around a plastic tube, 7.6 centimeter in diameter and 33 centimeter in length. Okay, so you would like to send a 3.0 amps current to produce 2.5 kilogram magnetic field inside your solenoid. What's the total length of wire you will need to meet this specification? The conversion factor is 1 Tesla is equal to 10 to the 4th Gauss. Okay, G stands for Gauss. 2.5 kg, that means 2.5 kilogauss. Okay, so let me switch my camera. Okay. All right. Let me give you guys a couple minutes for you to get started, and then we can look at the solution together in a couple minutes here, okay? All right. So let's take a look, okay? So in the previous slides, we said for a solenoid, if you want to know the magnetic field strength B is equal to either mu naught times capital N over L times I, or you can use B equals to mu naught times small n times I, where small n means turns of coils unit length, okay? So in here, what you are looking for is how long of the wire you should have, okay? So let's see here. You can sketch this, okay? So this is what you are going to sketch for the problem. So you can, assuming this is the plastic tube, you are going to wrap a lot of turns or coils around this guy here. All right, so we'll just indicate a few of them. Then you are sending the currents in here. Current will X out over here. All right, so the L will be this L, okay? This is the length of the solenoid by capital L here. And what you are going to do here, it's asking you what's the total length of the wire, okay? So the total length of the wire will be the length of this wire. So it should be measured from this end through each of the coils, okay? So total length of the wire, you can imagine it's not going to be the length of the solenoid, okay? So it's different. It's different from the total length of this guy because you can see each term will wrap around this guy, okay? So it will be 2 pi times r times n numbers you have over here, okay? So let's call this total length L. So this guy is the length of the solenoid, okay? And then this is the length, the total length, or let's say total length of the wire, okay? So this is what you are looking for, all right? You're not looking for that because that's already given, okay? So this is given as 33 centimeter. This guy is 33 centimeter is given. The I is also given. I is given as 3.0 amps. The B is given as 2.5 kilogauss. Okay, 10 to the 3 gauss. All right, this is given as 3. This is the constant. Okay, it's constant. You can plug it in. You are given this as 33. All right, you're looking for small l. Now, what will be L equal to? Small l. Okay, so if you have m turns over here, okay, assuming you have n turns, okay, n turns of coils, then the length L should be equal to m, okay, times 2 pi times the r of each, the circumference of each coil, okay? So it's 2 pi r, or it should be pi times d, either this guy or pi times d, okay? So it tells us the d, the diameter, so we are going to just use this one, okay? So we are going to use pi times, or n times pi times d, okay, for the length. We are given this guy, all right? So that means we need to look for this n, capital N, right, in order to solve for this guy. So, and we can solve for n, right, looking at this given over here, because this is given, this is constant, this is given, this is also given. So then this one you can solve, okay? So we are going to start from there. We are going to write that capital N is equal to, all right, we are going to do some algebra here. You multiply both sides by L, then divide both sides by mu naught I, okay? So this is what you're going to have. So N is going to be B times L divided by mu naught times I, okay? So then once you have that, then L is going to, small l is going to be equal to M times pi d, and will be B capital L mu naught times I times pi times d, okay? So then you just plug in all the numbers you have there. Okay, so you will have B equals to 2.5 times 10 to the minus 3 or 10 to the positive 3 Gausses. You convert it into Tesla because Tesla is the SI unit. Okay, Gauss is not the SI unit, but Tesla is. So 1 Tesla equals to 10 to the minus 4 Gauss. So that means you want to divide all this by, or divide this by 10 to the 4, okay, Gauss to get Tesla. Okay, so this is what you're going to do. This should give you everything in Tesla. Okay, times the L, 33 centimeter. So you want to convert it into meters. Okay, and then multiply by pi, multiply by the diameter. So let me just draw a line here. Times the diameter given as 7.6, again times 10 to the minus 2 meters. Okay, divided by mu naught is equal to 4 pi times 10 to the minus 7. Okay, Tesla times meter over m times I 3.0 amps. Okay, so you're plugging all these numbers in here. You can see there's this pi here will cancel out this pi. Okay, so you don't have to plug in the pi's into your calculator, but after that you can plug in the numbers into your calculator. Okay, so then after you plug in all the numbers, the small l is going to be equal to 5.2 times 10 to the 3 in meters. Okay, so if you want to have a magnetic field of 2.5 times 10 to the 3 Gausses, you indeed need a very, very long wire. Okay, so typically when you have a solenoid, the wire will be very thin. Okay, so it's going to be very, very thin wire. Okay, unfortunately, we are doing this online lecturing. We do have quite a few of solenoids in the actual classroom. Okay, so if we were in the classroom, I can show you guys how thin the wires will be on the solenoid, but we are not. So unfortunately, that's the case. But keep in mind, the wires you use to construct a solenoid should be very thin. Okay. All right. If you have questions, you can unmute yourself and you can ask me. Okay. So I will pause for a few seconds to see if you guys have any questions about this. Okay, so if not, then we are going to move on here. The last section in the textbook I want to talk about is the magnetic force between two parallel conductors. There's another section after this on the application of magnetism. I think we have kind of going through the applications already. So one of the applications in that section will be the mass spectroscope, and then the other one will be the velocity selector. So we have touched on those two already, but you guys can read that section yourself if you are interested. Okay, but this will be the last section we will be discussing in this class. Okay, so now up to this point, we know that if you have a current carrying wire, then you actually would have a magnetic field produced by that wire. Okay, so imagine if you have two wires, okay, like that, parallel to each other. So if you look at one wire, say this wire over here, then because this wire carries current, so you can see you can apply your right hand rule. You're going to align your thumb with the direction of current going up. Okay, so your forefinger is going to curve around that wire. So then you can see the circles indicate in the figure over here on the left. That indicates the magnetic field produced by the left hand wire here, or the left wire here. Okay, So now there will be magnetic field produced by this guy, by this wire in this region over here. You have a second wire that also carries current. Okay. Now in this region of the magnetic field produced by the left wire. So then the right wire here will experience magnetic force because there's magnetic field produced by the first wire. Okay. So then in that case, now you can use your the other right hand rule. Okay, you are going to again line your thumb in the direction of the wire. Now this time the second wire is also going up. Okay, your four fingers are going to be in the same direction of the magnetic field. So at that particular point, magnetic field is going to be in this direction. All right, going into the screen. Okay, on the position of the right wire. Okay, so the magnetic field produced by the left wire is going to be pointing into the screen. So this is, you are going to align. Okay, so thumb align with the direction of the wire, and then this is the direction of the magnetic field. So you can see the force, magnetic force, this second wire experience is going to be perpendicular to the palm. Okay, and then going in that way. All right, so that's what the right the figure in the right shows. Okay, so the figure on the right shows you on the second wire here, there will be magnetic force on the second wire. So F2 on wire 2 is going to be pointing towards the first wire. Okay, so you can see the direction of that. Okay, so in this case, you have two wires carries the current in the same direction parallel to each other. So the force one exert on the other will be attractive force. Okay, so that means if you have two currents, wires carries the current in the same direction, the forces on the wires will be attractive force. Okay, so similarly, you can analyze for the left-hand wire, what will be the magnetic force that left-hand wire experience? Okay, it's going to be towards the right wire. Okay, so the forces on each of them will be towards each other. So on one wire, there will be magnetic field produced by the other wire. So then there will be magnetic force on that wire. Okay, so now vice versa. So, but if you have two wires carries opposite current, so say one goes up, one goes down. Okay, so then the force between them will be repulsive force. Okay, they will repel each other away. Okay, so that will be the direction of the force. Okay. Now let's go back to the magnitude of the force, the magnetic force. Okay, so you can see for a wire carries current I, the force is going to be equal to this guy. So F. If you go a couple of sections back when we talk about a wire in the magnetic field, the force experience will be equal to the current it carries times the length of it, and then times the magnetic field experience. Okay, so then it's ILB. Now B in this case is produced by the first wire. So the wire carries current I1. The B field will be equal to mu naught I1 divided by 2 pi R. Okay, R will be the separation of the two wires. So you can see that will be the B field. So at the end, you are combining this expression. So you'll get mu naught I1 I2 times the length of the wire divided by 2 pi times R. Okay, so this will be the magnetic field on the wire if it has length of L. Okay, so more often or many times you will look at you'll be asked or you'll be given that force by so more often you'll be asking to solve for force per unit length. Okay, so that means more often you are looking for F divided by L. Okay, so then looking at the expression from the PowerPoint, then F by L will be, so you kind of divide the leftmost side, F divided by L. Okay, that's what this guy, and then the rightmost side by L. So then you get mu naught I1 I2 over 2 pi R. Okay, so more often you are looking at force per unit length. A lot of times you will be looking for false per unit length, or you are given false per unit length, okay, in that context, okay? So be careful about like what information you are given, all right? So this will be many times that the given quantities are the ones you are looking for, okay? All right. So again, we will take a look at one example here. I will give you guys again a couple minutes to get started on this one, and then we can look at the solution together in a couple of minutes, okay? And then in case if you have your answers, you can always send me your answers via the chart features here. You can, if you want everyone to see your answer, you can send it to everyone. If you just want me to see it, you can just send it to me privately, okay? So then only I will see your answer, all right? So take a couple of minutes to work on this one or get started on this one, and we can look at the solution together, okay? All right. So also, as I will take attendance of the class here, so if everyone can just send me, say hi to me, so I can save the chat later. I can see who's in, who's not, okay? Because if I look at this chat group here, I wouldn't know who's in here, who's not, okay? So please send me a message, say hi, just say hi. I will trace the attendance later, okay? Yep, you can say hello, that's fine. Yes, hi through this message, yes, got you. All right, if you haven't sent text message to me on this chat, so there's a chat feature of the Zoom. If you're on PC, you go to the top of your screen, you'll bring all the menu bars of the Zoom. You could click on more. There will be a scroll down menu on the top there says chat, okay? So you can send a message to say hi to me over there. All right. So let's take a look on this example here. This one says you have two long straight wires separated by a distance of 9.25 centimeter. Okay, so this tells you your R is going to be 9.25 centimeters. Okay, now it says one wire carries current 2.75, so that tells you I1. If we call the current in this wire to be I1, then it's 2.75 amp. Okay, it says the other wire we call that to be the second wire. It carries current of 4.33 amps. 4.33 amps. Okay, so A is asking us to find the force per meter exerted on the first wire. Okay, the 2.75 amps wire. So that means, see, this time we are looking for F1 over L. Okay, it's force per unit meter. Okay, so force per unit meter. So if we are doing that, then if we are looking at depth quantity, that means we are going to use this expression, okay, without L, okay, on this side. So force per unit length on wire one, we'll call it F1. Okay, so this is F1L. So the force we derived in the previous slide that applies to both wires. Okay, because both wires, they are interacting with each other. So this is a kind of force pair, action and reaction pair. Okay, so the two should have the same magnitude and opposite direction. All right, I think that just answers part B. Okay, so F1 over L is going to be equal to mu naught I1 I2 divided by 2 pi R. Okay, and then also F2 divided by L is also going to be equal to that. Okay, the same thing, because they are action and reaction pair. They should have the same magnitude but just opposite in direction. Okay, all right, so we are going to just plug in the numbers because we know I1 I2, we know R, the rest are constants. Okay, so 4 pi times 10 to the minus 4 Tesla meters over amps times I1 2.75A times 4.33A, okay, divided by 2 pi times the R 9.25 centimeters. So that means we want to convert into meters. Okay. Now 2 pi will cancel out 4 pi with 2 remaining because 4 by 2 is equal to 2. All right, so you can see many times you don't have to plug in the pi's because they will cancel out. Okay, so 2 times 10 to the minus 7 times 2.75 times 4.33 divided by 9.25 times 10 to the minus 2. Okay, so yeah, a lot of times I wouldn't apply the numbers in here. I would so here there's minus 2, 10 to the minus 2 here. I will cancel that out partially by that guy. So then that gives me minus 5. So a lot of times I will do that, but it's up to you guys. Okay, whichever you feel more comfortable doing, then just do as you like. So then I'll be doing 2 times 10 to the minus 5 times this 2.75 times 4.33 divided by 9.25. Okay, so at the end, then this will give me the F1 divided by L, force per unit length equals to, I have calculated this before, this is going to be equal to 25.7 times 10 to the minus 6, okay, newtons, or actually, because I'm using 10 to the minus 6, because then I can express in terms of 25.7 micro newtons, okay, or if you plug in all the numbers, you should get this should be per meters. Okay, per meters. You should get 2.57 times 10 to the minus 5, okay, newtons per meter. Again, that should be your answer, but either way, okay. Either this one or that one, doesn't really matter, okay. So this is the magnitude for the force exerted on the wires, okay. Now for the B here is asking, is the force per meter exerted on the second wire greater, less, or the same, okay, in magnitude? This should be the same because the two forces they are action and reaction pair, okay, same magnitude, okay, should be the same, right? Because action and reaction pair according to Newton's third law, okay? All right, questions you guys might have on this one? If not, then we are going to look at the second example on this topic, okay? Now, a lot of times you have multiple wires close to each other, okay? So in this example, you have 3 wires carries current. So 1, 2, and 3, okay? So you have 3 wires here, they carries currents. Now, in this problem, it's asking what would be the direction and magnitude of the force per meters that the top wire experience in the figure. Okay, so this guy here. So on this one, this is a solenoid. It's actually no, it's equilateral triangle on the geometry here over here. Okay, so because the 3 sides are the same, they are all 10 centimeters. Okay, so it's a equilateral triangle there. So let's take a look here. On the top wire here, and then bottom wires. Okay, so the cross means that currents are going into the paper. Okay, on the top here is a dot, that means the current is coming out of the paper. Okay, now we are looking for force on the top wire here, so that means we'll be looking for the force by the bottom 1 wire here and then bottom 2 wires here on the top wire. Okay, so between the top wire, let me call it 3, between 3 and 1, you can see on the bottom here, the current points into the paper. On the top here, it comes out of paper, so they are in opposite direction. Okay, so then the force between these 2 wires should be repulsive. Okay, so there'll be one force on the 3 wire here that's going into this direction, away from the 1. Looking at the forces between 2 and 3, okay, on 3, again, those 2 currents are in opposite direction, so then the force between them will be repulsive force again. Okay, so this guy will be F2. All right, so F1 and F2, they are vectors. Again, you guys don't like vectors too much, but unfortunately, it looks like we couldn't just get rid of it. Okay, but these are 2 forces on the 3 wire. So then the total force on the 3 wires should be equal to F1 plus F2, okay, in vector form. Okay, now for vectors, then we're just doing the x and y component. Okay, so we'll take here, we will set up an x component and y component. Okay, we will set x component to be to the right horizontally, y to be vertically upward. Okay, so then this angle, we know it's going to be 60 degree. Okay, this angle should be also 60 degree. Okay, so then we are going to do these 2 vector addition. We are going to need to find out the x component and y components. Okay, and then also we would, because we know these 2 angles, we know like directional angles, then we also need to know their magnitudes. Okay, so for the magnitude, we'll apply the equation. Okay, so F. Now in this case, we are also looking for F per meter. So that means F over L. Okay, so F1 over L, F2 over L. Okay, so we are going to be looking for F divided by L, and then F1 divided by L plus F2 divided by L. Okay, we are just going to assume L is equal to 1 meter because that's what we are looking for, force per meter. Okay, so let's say just F equal to, or L equal to 1. So then we will just be doing F1. Okay, that should be equal to F1L, or just look at F1L, should be equal to mu naught I1 I3. Okay, 2 pi r. R will be 10 centimeter. Okay, I1, I3 is the currents between them, the two wires. Okay, so we are going to plug in the numbers. So this is again 4 pi times 10 to the minus 7 Tesla meters over amps. I1 it's given as 5, or actually 10 amps. I3 is 5 amps. Okay, divided by 2 pi times 10 centimeter. That means 10 times minus 2 meters. Okay, that gives you meters. All right, so this is equal to 1 times 10 to the minus 4 meters, or newtons per meter. Okay, the magnitude of F2 per L per unit length is going to be mu naught I2 and then I3. Also divided by 2 pi times R will be the same because it's equilateral triangle. Okay. So 4 pi times 10 to the minus 7 Tesla meters over A. This time A2 is equal to 20 amps. I3 is also still 5. 2 pi times 10 times 10 to the minus 2 meters. Okay. If you plug in the numbers here, this time it gives you 2 times 10 to the minus 4 newtons per meter. Okay. Now we will look at the X and Y components because that's what we are needed. That was just what we need. Okay, so F1 X, okay, should be divided by L. Okay, again, you can assume L is equal to 1, then you are looking just at F1 X. Okay, so X component should be equal to F1 L times cosine of theta 1, which is 60. Okay, so F1 over L. Oh, let me just take the numbers. 1 times 10 to the minus 4, okay, cosine of 60, that would be equal to 0.5 times 10 to the minus 4 newtons per meter. Okay, this is F1x, or F1 over Lx. F1y over L should be F1 over L sine of theta 1, okay, 1 times 10 to the minus 4 newtons per meter sine of 60, that should be equal to 0.866 times 10 to the minus 4. Okay. Now for F2x component, okay, F2x component per unit length. Now on the figure here, you can see F2 is pointing in this direction, okay? So then its X component, if you just want to use this angle, all right, then it will be, you are looking at this X component, okay? It will be negative of this times cosine of 60, all right? You can also follow what we had for the first semester. If you just do F2 cosine of the angle theta 2, then you will be looking at this angle, all right? So then you'll be looking at 120 degree, all right? So either way, so this time I'm going to just look at the geometry directly. So then you will tell it's going to be negative, okay? Negative is going to be negative of the F2, the magnitude over L cosine of the 60 degree, okay? So minus, if you plug in the numbers, will be minus 2 times 10 to the minus 4, okay, cosine 60. This time it will give me 1 times 10 to the minus 4, okay. F2YL, okay, I'm going to speed up because we are running out of time. So then looking at the geometry would be sine, okay. You are going to take in this number again, but positive sine of 60, then this will give you 1.732 times 10 to the minus 4 meters per second, per meter, newtons per meter, okay? So then at the end, the total force F we are looking for over L, its X component should be F1X plus F2X, okay? Over L per unit length, you are going to take in the numbers 0.5 times 10 to the minus 4 plus 1.0, or actually that's minus over there, minus 1.0 times 10 to the minus 4 newtons per meter. Okay, that will be minus 0.5 times 10 to the minus 4 newtons per meter. and then the y component over L is going to be equal to F2y or F1y L plus F2y over L. Okay, you're going to take in the y component of the first one times 10 to the minus 4 newtons per meter plus 1.732 times 10 to the minus 4 newtons per meter. Okay, so then it gives you 2.598 times 10 to the minus 4 newtons per meter. Okay, so now you have its x component and y component. So then the magnitude will be the x component square plus the y component square. Okay, you're going to plug in the numbers. I'm going to just tell you what's the final answer: 2.65 times 10 to the minus 4. Okay, direction angle, because we are looking for magnitude as well as direction. Okay, tangent or theta equals tangent inverse of Fy divided by Fx. Okay, so it's going to be giving you, when you plug in the numbers, minus 79.1 degrees. Okay, but our x component is less than 0, so we want to add 180 degrees. Okay, because of that. So 100.9 degrees. Okay, so yeah, a little bit tedious. Okay, but again, we should master this. Okay. All right, time for questions, if any. So if not, then we are going to see you guys on Wednesday. Okay, so remember, homework 7 is still on Wednesday. Okay, and then on Wednesday in the afternoon, some of you guys will have lab. We will also meet on Zoom. Okay, I will send you guys link later on. Okay, so if no questions, then see you guys on Wednesday. Bye.